Welcome to what is the last lecture on X-ray diffraction. Before we go through the slides, I want to point out that this is, I believe this is set number 12 of all the lecture slides. I think it's the 6th set of slides related to X-ray diffraction. I believe I sent these slides out at the beginning of March. Over the weekend, I actually redid a whole bunch of these slides and took out the whole last portion of this set of slides that I sent to you several weeks ago. So when I send out the link to this video, I'll also send out the PDF of the slides themselves. So you might want to overwrite the previous ones with this one because they are different, although not substantially different, but more applicable to the current suite of software that exists at Rutgers. Anyway, onward. So first we'll talk a little bit about the underlying principles of Rietveld refinement. All right, the Rietveld roadmap actually consists of many somewhat complicated individual steps. There are many shortcuts if you already know something about the sample of interest, and the ultimate goal is to obtain a final structural solution. However, for most of us, the goal will be to use the refinement of existing structures to quantify and characterize your samples. But really, the Rietveld refinement itself is designed as something for crystallographers to use. To refine information to get them to a final structure solution. And over here on the right-hand side is a fairly complicated maze that starts with the sample itself, then walks through obtaining a diffraction pattern, goes through a series of complicated steps to ultimately get to a structure. Okay, and then once we get to that structure, they use the Rietveld refinement, which is the refinement of all these parameters within the structure to get to a final structure solution, which is something, like I said, a crystallographer might use. You will not go through all these steps. You will obtain a diffraction pattern, and then you're going to use existing structures that are available in databases to do your analysis, to hopefully provide you quantitative and other characterization aspects of your samples. So what do we get for all this trouble? You can read the list yourself. You can see that there's a lot of information you can get out of a Rietveld refinement. As for the most part, as you go down the list, obtaining that information becomes more and more complicated and can involve complicated analysis and special setup to actually do the Rietveld analysis properly to give you that information. But for the most part, the people in this class should be aware, and what's important about this is you can get lattice parameters out of it, you can get quantitative phase analysis, grain size information as we've talked about it. Ultimately, if it's important to you, you can also get atomic position and atomic occupancy information. Additionally, as I think we've discussed in class, you can also obtain sort of a degree of crystallinity. So I think these 6 items it's important for everybody in the class to know that this kind of information is available, that you can get relatively easily from a Rietveld refinement. And then obviously, if you want to do more advanced techniques, you can get some of the other information that you see on here. So what do we need to actually get started on a Rietveld refinement? Well, first and foremost, we need a step mode scan, set of step mode scan data, which is nothing but a fancy term for an XRD pattern, okay, which we've talked about at great length. Usually the 2 theta value should go from 10 to 120 degrees or more with a step size of at least 0.02 degrees or better. Going to 120, 130, 140 degrees is really only necessary if you're going to do advanced techniques like strain analysis, and things of that nature. If you're doing simple quantitative analysis, and even for that matter, precision lattice parameters of known structures, then a 2 theta range from 10 to 80 or 90 degrees is fine. As I think we've discussed in some previous lectures, sometimes you may need to start your scan at less than 10 degrees, even down to 3, 4, 5 degrees if you've got some peaks down in that region, which you would know by obtaining a quick scan. With regards to lattice parameters, sometimes it is important to get peaks out past the 80 or 90 degree range to get good precision lattice parameter measurements. As we've discussed previously, the counting time is instrument dependent. You want sufficient counting time that you have at least 10,000 counts in your strongest peaks. If you have a complicated pattern, with many peaks and overlapping peaks, it's probably advisable to get the counts substantially higher than this. In most of the Rietveld refinements that I do in my lab, I would say that the strongest peaks are probably on the order of 60, 70, even 80,000 counts. And then you need some kind of an initial structural model having roughly accurate lattice constants, the correct space group, and approximate atomic positions to do the refinement. And then, of course, the idea behind the refinement is it will get you closer to your ultimate structural solution. You can break up a Rietveld refinement into sort of three subsets or three sub-models, if you will. There's a basic crystallographic model that describes the size, the symmetry of the unit cell, the atomic positions, thermal parameters, and site occupancy. This is all of the information that will actually come out of the various databases that are available, that you'll download the structures and use the data in those structures to refine to develop a more precise crystallographic model. You also need an instrument model. This describes the optics and the basic setup of the diffractometer. This can be important for more advanced techniques. Specifically, if you're going to estimate the crystallite size of your sample, you have to have some understanding of the instrument portion of peak broadening to do it. If you're just doing quantitative analysis, the instrument model really isn't as important. And lastly, there is a profile model, which basically describes the peak shape. And we'll talk a little bit about, or probably mostly about, the profile model itself. The crystallographic model, for the most part, you're going to download from a database. The instrument model you'd have to obtain if necessary, and the profile model is actually what most of the Rietveld refinement for you is all about, in addition to things like lattice parameter and scale factor, which we'll talk about in a little bit. So how do we obtain an initial model? You can obtain these known structures from databases such as the CSD, the ICSD, the Pauling file, which is part of the powder diffraction file. You can get this information from open literature. Sometimes structural information is actually published as part of the supplement in academic literature. Any source that has a prospective model is worth considering. You should keep in mind that solid solutions usually adopt the same structure types as their parent compounds. We talked about this in one of the lectures. An example of it is that sodium chloride, which is salt, and potassium chloride have exactly the same structure and can actually substitute for each other. If you were to look at the diffraction pattern for these two compounds, the diffraction patterns look very, very similar, but they're spaced apart because of the difference of the atomic sizing. All right, but you can substitute potassium for sodium, which will cause those peaks to move. So again, a solid solution will use those same structures. The idea behind this is that if you can't find a precise structure for whatever it is you're looking for, you might be able to substitute something else for it. Compounds with the same chemical formula. This sometimes is true, but not always true. An example, of course, is here we've got listed yttrium, barium, copper oxide, right? You might be able to use the structure file for that as a prototype model for neodymium, barium, copper oxide. It is not always true. And then we have an example of a case where it isn't true. It is very typically true if you're dealing with rare earth elements that substitution works pretty well as prototype models. Obviously, you can do trial and error in terms of models. For most of you, that's not going to work. And then you can obtain an initial model from thermodynamic models. This is the part that you really care about. Is the crystal structure actually known? I think we probably talked about this in one of the previous lectures, but here it's a little more formalized in a slide. There are probably three principal sources for good, accurate crystallographic data. One is the ICSD, which is International Crystal Structure Database. It actually comes out of Germany. Currently, there are over 200,000 entries in this. It's primarily minerals and inorganic compounds. Then there's the Cambridge Structure Data Bank or database, which is sometimes referred to as the CSD. There are over 1 million entries in this database. They're primarily organic and organometallic compounds. The problem with this particular structure database is you cannot search the database using an existing pattern. like you can with the ICSD database. You can do that. You can do a search match on your pattern and try to identify things in the database. Where the Cambridge structure database, you have to kind of know what you're looking for. You go look for it, and then you download that structure file. And then last but not least is the ICDD diffraction data. This is the powder diffraction file, or referred to as the PDF. This is probably the most commonly used thing in the United States. And it's probably at this point the most comprehensive source of diffraction data. So I'll kind of highlight that this is the thing that most people use. All right, there's actually two components to it. There's what's referred to as the PDF4 Plus. It has over 400,000 entries, and those are primarily inorganic. And then the ICD publishes a separate database referred to as the PDF Organic, which has organic compounds, pharmaceuticals, and so forth. The NIST also publishes a crystal database. This crystal database was actually published initially in conjunction with the ICSD. That's currently in flux, so I don't know if that database is still available. The ICSD and the ICDD database are both by subscription. They're quite expensive. The Cambridge structure database can be accessed freely on the internet. Currently, we actually have the PDF in the lab downstairs in CCR. If you don't want to spend money on a database, there actually is a free database called the Crystallography Open Database, or referred to as the COD. And the internet site is posted on the slide, www.crystallography.net. There are over 400,000 patterns in this database. They have a fairly comprehensive set of inorganics, but I would say the bulk of the entries are probably organic. But you certainly could use this database just to learn how to use or analyze XRD patterns and perform basic Rietveld refinements without spending the money. And for the most part, the mineralographic and inorganic portion of the database is really more than sufficient for doing basic analysis. So a free option. So I guess the point of this slide is to actually discuss what is a Rietveld refinement, all right? And the Rietveld method consists of refining a crystal structure by minimizing the weighted least squares difference between the observed and calculated pattern against some parameter vector, all right? Ultimately, there are probably 100 parameters you conceivably could refine. And this is sort of described by this chi-squared equation seen on the screen. And it's kind of self-explanatory, right? So you've got some weighting factor times the difference between y sub I, which is an observed intensity, minus y sub ci, which is a calculated intensity, based on the structure and whatnot of the compound of interest, times some parameter to be refined, all squared, and then summed up across the pattern. And of course, the idea is to minimize this chi-squared value. Ideally, the chi-squared would equal 0, which means that your observed intensities and your calculated intensities across the pattern are exactly the same. So that's the objective of it. The next several slides probably, or 15 slides, will probably have a lot of math on them. For the most part, I don't expect you to really know the math or learn the math. It's just important to know that the math is out there, and that the math sort of explains why we refine some of the underlying parameters. So the computed intensity, all right, y sub ci, which is our calculated intensity, is a combination of many things. Ultimately, it goes down to this intensity function here, which is really not that dissimilar from something we looked at in class a couple of lectures ago, where the intensity is a function of the Lorentz polarization factor, the structure factors, absorption factors, potential preferred orientation, and a number of things. And then ultimately there's also an S in here, which is a scale factor, which describes how much of something is in it. So we use all of the things that drive our intensity, we apply a scale factor to it, and that's how we get our quantitative analysis out of it. The ultimate goal, as we discussed a couple slides ago, is to minimize the least square difference between the observed and calculated intensities. All right. And so what this does is it provides values of parameters constituting the local minimum closest to the starting point. All right, obviously if we were to graph this in 3 dimensions, we would get a fairly complicated series of hills and valleys. You do want to be careful because it's possible to get caught in a false minimum in this model. So when we do a Rietveld refinement, you want a good set of starting values for all the parameters. So what that means is you want the crystallographic model that you select so that you download the database to be as close to your pattern to start with as you can get. Similarly, when you start a Rietveld refinement, you want the positions of the peaks, the scale factor of the peak, which you can actually manually set before you start to be as close to the pattern as possible. If the initial model is bad, the procedure will not converge and it actually may diverge, and the Rietveld refinement will kind of blow up on you. All right, so now we're going to show some of the details. This is the part that has all the math in it. I'll go through it pretty quickly. Again, and you're not responsible for the math. I just want you to understand that these are all things that you can refine as part of a Rietveld refinement. You don't have to refine all these. You make decisions about what to refine and what not to refine. I think we previously talked a little bit about backgrounds. For the most part, backgrounds are determined in one of 3 ways. You can specify a background function, which is just usually some high order polynomial. All right. You can do a linear interpolation between user selected points in the pattern. And that's where you just basically are sort of picking points at the bottom of the pattern and then using some kind of interpolation function to draw the line between those points. Or you can use some kind of user supplied function. And that's usually a Chebyshev polynomial. And then this math equation on here is just to sort of show that you're summing the background positions across the entire pattern. All right. When I do my Rietveld refinements, I, for the most part, use a linear interpolation between user selected points in the pattern. At the end of this slideshow, I'm going to reference a video demonstrating a Rietveld refinement. So you'll see what I mean by fitting a manual background. In addition to the background, all the things we previously talked about can be set up as parameters to refine. One of them is the polarization factor and ultimately the Lorentz polarization factor, which also includes impact on absorption characteristics. We're not going to really talk about this. The graph on the right side sort of demonstrates the impact of the Lorentz polarization factor as a function of the Bragg angle. The software that does the Rietveld refinement, for the most part, the default setup in terms of refinement is usually sufficient for most applications. So we're not going to really get caught up in this. The temperature factor, again, we've discussed this before. You can actually refine what are referred to as the B ISO values, which are the temperature factors. Just so that you understand what the temperature factors does, on the left-hand side, or the left plot here, shows what the peaks might potentially look like if you had no thermal vibration involved. But once thermal vibration starts, all right, this results in expansion of the unit cell, okay, which will cause the lattice parameters to be larger and they shift in the 2 theta positions. It will result in a decrease in the intensities of the diffracted lines, and it will result in an increase in the background intensity. And so the plot on the right-hand side sort of shows what a potential plot might look like with and without thermal vibration. For the most part, I don't think you need to worry too much about temperature factors. However, sometimes you may do a Rietveld refinement and find that the refinement doesn't work well for you. And if you were to investigate how the structure was solved in terms of the structure file that you've brought in from the database, you may see that it was done at a liquid nitrogen temperature, where you took your powder sample at room temperature, and if the difference between the thermal vibrations done at room temperature and liquid nitrogen temperature are substantially different, all right, it may actually impact your pattern, and you may want to consider refining the temperature factors. Crystallite size effects, we've talked about this at some length. All right, we know that from the shear equation, there's a relationship between the full width half max of our peaks and the size of the crystallite given by the shear equation, which is the first equation on there. This also, comes into effect in terms of how it's calculated depending on whether your peak shape is Lorentzian or Gaussian. If it is Lorentzian, then the total B value in the shear equation is actually the sum of the B value from the size of the crystallite and the contribution to the peak broadening from the instrument. If it's Gaussian, it'll actually be the square of those values. So it's just something to be aware of. This is where the instrument profile matters in terms of crystallite size, because obviously to accurately calculate the crystallite size using the shear relationship, you need to know that B instrument value, which is something we haven't really talked about how to acquire it, but just be aware of it. So here are some profile fitting functions. The top formula shows the Gaussian function. The bottom one shows a Lorentzian function. In reality, almost all peaks are some combination of the two. All right. We're not going to talk about the equations, but the refinable parameter in these equations, depending on which one you select, is this HK value. There, and so forth. This HK value is actually the number that we're refining, and the HK value is just a nomenclature for the full width half maximum of the peaks. So that you understand the difference between a Gaussian peak and a Lorentzian peak. Generally, the Lorentzian peaks have the tails sort of broaden out in a flatter way. So the peak comes down and they don't tail off quickly, whereas the Gaussian peak sort of has a sharper bend in the bottom. So here's a plot sort of showing the difference between a Lorentzian peak and a Gaussian peak. And in this particular case, the HK value, or full width half max, is 0.2, and I should have a degree marker in there. 0.2 degrees. Okay, so that's the difference between a Gaussian and a Lorentzian peak. As I said, all peaks are actually some combination of Gaussian and Lorentzian. There are actually two sort of common profile fitting functions that Rietveld refinements use. One is referred to as a pseudo-Voigt function. The other one is referred to as a Pearson 7 function. Both functions operate pretty similarly, and both are basically some combination of Lorentzian and Gaussian. And you can kind of see from the formulas on the right side that you have some shape factor, which is a function of an initial shape factor, plus another function as you move through 2 theta. And what that shape factor does is provide a weight to the Lorentzian, and as you can see, the Gaussian portion of it is 1 minus that weight. So you end up with a percentage Lorentzian and a percentage Gaussian based on some initial shape factor. And so here is an example using pseudo-Voigt functions. Once again, the HK value, which is our full width half maximum, is 0.02 degrees, which is actually a fairly broad peak, by the way. And this is really just to demonstrate the point, so you can actually see it in the pattern. And then you can see the various plots where you vary the percentage of Gaussian and percentage of Lorentzian. So in the case of the green plot, you can see it's primarily Gaussian, and the tails cut off rather quickly. Whereas in the black plot, where you're 0.3 or 30% Gaussian and 70% Lorentzian, the tails approach the asymptote a lot more slowly. So that's sort of the difference between the how the pseudo-Voigt function would apply. And then the other profile fitting function is referred to as the Pearson 7. Again, a rather complicated formula, which we don't care about. And there are several parts of this formula that we can refine: HK, M naught, X, and Y, which we're not going to really discuss those. But at the end of the day, just like the pseudo-Voigt, it results in some combination of a Gaussian and Lorentzian fit to the peaks. All right, so that defines the shape of the peak. But we also, as part of the profile model, have to create some method for determining the full width half maximum of our peaks. In JADE, there's 2 possible restraints for the full width half maximum. One is a second order polynomial given by the equation on the right, where the full width half max is equal to some F naught value plus an F1 value times 2 theta plus F2 times 2 theta squared. So you can just sort of see that potentially goes up to a second order polynomial. By the way, when you look at an equation like this, and you see terms separated by a plus sign, you can actually select, you know, 1, 2, or 3 of these terms. So in this first model, we could actually define the full width half maximum as just being a constant, F naught, all right, or F0, which basically means you're going to just set the full width half max as being constant across the X-ray diffraction pattern. Is that accurate? No, because it actually does broaden out as a function of 2 theta. So you really, for the most part, want to incorporate F1 and F2 into it. Sometimes for phases in an X-ray diffraction pattern that have very weak peaks where you can't see the secondary peaks, then it's just easier to set the full width half maximum at a constant because you can't really see those peaks anyway, and it prevents the Rietveld refinement from sort of blowing up on you. Alternative to this polynomial is what's referred to as the Cagliati function, where the full width half maximum is defined by these u, v, and w parameters. U times the tangent squared of theta, v times tangent of theta, plus a w parameter. I think on the following slide, there's actually a plot of what the typical full width half maxes in the diffraction pattern look like as a function of 2 theta in terms of their breadth. And you will see that the peaks broaden out substantially once you get past 80 or 90 degrees 2 theta. If you're doing a lot of work in the high 2 theta region, and you're running your plots out that far, that's where the Cagliati function puts more emphasis on the high 2 theta region. So here's the plot I was referring to. So if you look at, I guess it's blue or black, I can't really tell the color, is the typical variation of the full width half max as a function of 2 theta. And you can see starting from 10 to about 80 degrees, the full width half maximum of your peaks is relatively constant, right? But then at about 80 degrees, it starts to increase. And then by the time you get to, you know, 110, 120 degrees, the full width half max increases a lot. So for the most part, if you're just dealing with a XRD scan in the range of, say, you know, 10 to 80, 10 to 100, the simple polynomial and even the constant may be more than adequate. If you're going to go out farther than that, then you probably want to consider the Cagliati function. So in addition to all the various profile functions, we can also refine parameters to account for preferred orientation, which we've talked a lot about in class. The most common method for doing this uses what's referred to as the March-Delassi function, shown here on the right as a rather complicated formula that's referred to as the modified March model, where G1 and G2 are refinable parameters in the refinement. You don't need to understand the math behind it. The point is when you're doing a Rietveld refinement, you can select to refine these parameters. All right, and then when you refine this, this value is going to go up or down, and you'll get an ultimate value. The closer this value is to 1, it suggests that there's no preferred orientation. If the value is substantially less than 1, it supports the idea of a platy habit. Habit means a crystal structure where they form plates. And if this G1 value is much greater than 1, it has a needle-like habit. But just be aware of the fact that if you see preferred orientation, you can refine it to help adjust your model to account for it. Then there's also what's referred to as systematic line shifts, which are a function of the Bragg-Brentano geometry. The two of them being specimen or sample displacement, the other one being specimen or sample transparency. I'm pretty sure we talked, and there was a slide on specimen displacement given by the function on the right, where S is the actual displacement up or down from the eccentric plane of the diffractometer. R is the goniometer radius of the diffractometer times cosine of theta. What that basically means is if your sample sits a little bit above the plane of the diffractometer, it's going to shift your pattern to the right a little bit. If it sits beneath that, it's going to shift the pattern a little bit to the left. This obviously can be geometrically derived to get the equation that you see on the right. And because it's a systematic line shift, the Rietveld refinement is actually able to hopefully identify that line shift. Similarly, there's what's referred to as specimen transparency. Same basic concept of displacement. You can get a shift to the right or a shift to the left of your sample based on specimen transparency. And what specimen transparency is, different compounds have a different linear absorption coefficient. The linear absorption coefficient of a sample is the abilities of the X-ray to actually go through that material. A low value means that it's relatively transparent, which is the mu value down there. And a high value means it's relatively opaque to the X-rays. So obviously, if you have a very light sample like an organic material, the linear absorption coefficient is going to be very, very low. All right. So the X-ray beam is going to go through that diffractometer plane and actually diffract deep into the sample, which will cause a systematic shift in the pattern. So these can both be refined as part of a Rietveld refinement. There's also what's referred to as an asymmetry profile correction. For the most part, these corrections are automatically turned on by default whenever you do a Rietveld refinement. You do have the options of selecting how far into these equations you go, meaning you could select, P1 and P2 or P1, P2, P3, and so forth. But like I said, unless you're doing advanced fitting, for the most part, you're just going to rely on the default settings. But again, know that the function exists. If you see strange asymmetry in your patterns, you may want to consider adding or deleting some of the parameters being refined. This comment on the bottom, this asym lim, is actually a box I probably should have taken out because it relates to the old software that these slides were originally based on. But it's probably worth noting why it's there. Peaks below a certain 2 theta angle in the pattern, you will see a high degree of asymmetry. All right, and that's a function of the radius of the Debye ring. I think we've previously shown that a diffraction pattern is a slice of the Debye rings. And when you're at very low 2 theta values, those Debye rings have a very, very small radius. And so when they pass through the slit, you get a substantial change in the intensity of the peak as that radius passes through the slit. So in the low angle regions, from 5 to say 20 degrees, you get a very high degree of asymmetry. So the peaks are all skewed to the left-hand side. So for the most part, you always correct for asymmetry in the low angle region of your patterns. Once you get past 20, 25 degrees, that asymmetry starts to go away as the radius of the Debye rings becomes larger and larger and larger. Then there's also lattice site occupancy. Obviously, you're going to have some starting model that's going to have an occupancy, but you can refine the portion of that occupancy so you can change it. Obviously, you have to have full occupancy for your model. So if you're going to refine, just as an example, how much potassium occupies a particular spot, that will have to be offset by a corresponding occupancy somewhere else. But just know you can actually go into the refinement controls and refine the lattice occupancy. And last but not least, there are several agreement factors. Another way to think of this is these are basically the quality of your results, or a residual error is probably a better term than agreement factors. And there's several different ones, different packages. You use different ones. JADE uses a weighted average residual error, but you can go through these formulas themselves. You're not responsible for them, but you can actually see, for the most part, in some form or fashion, it is the difference between the observed intensity and the calculated intensity, divided by the sum of all the intensities times 100. In one case, you square it and then take the square root. In other cases, just a direct profile factor and so forth. We don't really need to talk about those. But whenever you do a Rietveld refinement, there is some type of residual error indicator, and you obviously want to minimize that value. So the lower the residual error, the better quality refinement you hopefully have done. So now we're going to talk a little bit about quantitative analysis. Quantitative analysis can be kind of summarized in this, ugly looking function up top where the weight fraction for the jth phase is equal to all the various things that go into that phase. And you can read the slide, I don't really need to go through it, divided by the sum of it, the sum of that for all the various phases of interest. All right, I've mentioned the term scale factor before. Ultimately, this scale factor value, this S sub j, is the value that you're going to refine, because things like the unit cell volume, the mass of the formula unit, the number of formula units per unit cell, and so forth are really going to be derived directly from the structure of the phase of interest, but that scale factor is going to take that data and multiply it times an S value, which drives the quantitative analysis. So here is an example of a quantitative analysis. This is actually from the old set of slides. So this was actually done in full prof or GSAS. I don't really recall. I haven't used them in a lot of years, but at least demonstrates what a Rietveld refinement sort of looks like. You sort of see two plots in here. You see a series of red dots, which are actually is your observed or experimental diffraction pattern. So that's the pattern you generated. And then you see a black line plot, which is the calculated pattern using the structure files that you would have gotten out of one of the databases. And then you see down at the bottom of the plot is a blue plot difference, if you will. And that blue line is the difference between each point, y observed, y minus y calculated. And obviously the ultimate goal of our Rietveld refinement is to get that blue difference line to be a flat line or very close to it. The green hash marks in this diffraction pattern are indicative of where the various peak positions would be for each of the two phases. So the guidelines for a good quantitative analysis, the sample should be homogeneous. That's actually true for really any kind of sampling or any kind of analytical technique that you do. Sample should always be homogeneous. You must have sufficient number of grains with random orientations, and I think we talked about the number of particles that exist in a particular sample before, based on the particle size and a function of the sample holder itself. So you want to have a good sample, and the structure of all the phases should be well known to do a good quantitative analysis. There's a suggested turn-on sequence when you do a Rietveld refinement. The thing you have to remember about a Rietveld refinement is it's a complicated model with a large number of parameters that can be refined. In theory, you could just go in and say sort of turn on every single parameter to refine it. But because you're doing a minimum least squares fit to an existing pattern, turning on things may actually cause the model to converge inappropriately, giving you incorrect data. Alternatively, it can actually cause it to diverge and sort of blow up. Meaning it crashes on you. It'll come up and tell you, that this thing has crashed. So what you want to do is you want to do your refinement from sort of the most basic parameters to the more complicated parameters. And when you have a sufficiently satisfactory refinement, meaning that difference pattern is as close to a flat line as you think you can reasonably get, you stop. You don't keep refining parameters just in an effort to take away small deviations between the observed and calculated line intensities. So there's sort of a suggested turn-on sequence that people suggest for doing a Rietveld refinement. And so typically you want to refine your lattice parameters and your scale factors first, right? Those are sort of the obvious things. The lattice parameters dictate where your peaks are going to be, and the scale factors are going to roughly dictate how tall the peaks are going to be. Then you want to account for any sample displacement, okay? Then you want to account for any background or refine the background if it's not manual. I think I previously mentioned I always leave my backgrounds manual because I find that the various background fitting functions really don't work that well. Then you want to refine the full width half maximum, and then the shape. If at that point you still aren't satisfied with the quality of the refinement, you can start going into things like atomic coordinates, temperature factors, and occupancies, and also preferred orientation. I would tell you preferred orientation is typically pretty obvious if you've properly identified all the phases in your sample, and you probably can turn on preferred orientation somewhere in the same position that you turn on the full width half max and the shape factor. And this is just a suggested turn-on sequence. You don't have to follow it. What's also important is before you start a Rietveld refinement, you want to manually get your model to be as close to the existing pattern as possible. Again, this is to avoid a false minimum. Some factors that can affect refinement results. If your instrument resolution is too low, and that little thing saying RS equals 0.1 or 0.2 millimeters, that's the receiving slit. I think we talked about the effect of the receiving slit on resolution of the instrument, having too broad a slit in the receiving side of it can cause your peaks to broaden. Obviously, if the resolution is poor, you might not be able to properly deconvolute peaks or separate peaks or even identify peaks. So poor instrument resolution will affect refinement results. If the counts are too low, it'll affect refinement results, and obviously you may have trouble quantifying phases that are present in small quantities. Too little sample. The sample should fully cover the sample holder or fill the sample holder. If you're backloading it, you want the sample to be as densely packed as possible. That frankly will affect the number of counts that you get, and also ensure that you have a randomly oriented sample, or help ensure it. You want to be careful of beam overflow in the low angle region. Beam overflow in the low angle region basically means, I think we talked about the fact that the beam diverges as it approaches the sample. At low 2 theta values, the beam will actually spill off the sample and come off the sample holder. The expected intensities of the peaks, as you would calculate them using the structure data that you get out of the databases, assumes that the beam is only being diffracted off the sample. And so what that means is if you're using too broad of slits on the diffracted, not on the diffracted beam side, but on the incident beam side, that the low angle peaks the intensity of those peaks could be too weak because the beam's not actually hitting the sample, but it's hitting the sample holder. It's also possible to refine too many parameters, which leads to a false minimum. I mentioned this before, so you don't want to just turn everything on. An improper profile function won't fit the peaks properly. So like you can go into refinement and select Lorentzian or select Gaussian, absolutely, and not fit the peaks properly. And then of course, improper fitting of the background will obviously affect the results. So I know sitting through 40 minutes of me talking to these slides probably doesn't seem very useful because you've never really seen one. So what I've done is I removed all those old slides from the previous set of slides, and I decided to just actually take a real sample from one of my customers and do a refinement. So I actually started from scratch. I opened the file, I fit the background to it, I do a search match on it. Unfortunately, I did it at home this weekend, so I didn't have access to the PDF. So I had to use the COD, the free database, but like I said, it's sufficient for this kind of analysis. So I did a search match, I identified the phases, and I tried my best to walk through a step-by-step Rietveld refinement and try to sort of show what I mean by turning on or turning off parameters. The name of the video file is titled Rietveld Demo Video on Gypsum Sample, so I will upload that to YouTube also and include the link for that. I've never actually tried doing this before. Typically if I'm sitting in my lab and I do a Rietveld refinement, I just open it and I work pretty fast and I get it done, and then I give my customers the results. So I tried to walk through this in a stepwise fashion, and I hope it was worthwhile as opposed to a bunch of slides. Please let me know. If somebody has questions or wants to see me try a different sample or something else, I will be happy to make another video of it. So please make sure you download and watch the Rietveld demo, because it's part of this lecture. In terms of understanding what I would expect you to be responsible for with the Rietveld, you certainly aren't expected to know the math behind it. I said a number of times, really the point of the class is for you to know the characterization techniques so that when somebody asks you to do something, you know what technique will get you there. So if someone were to say, you're going to do a doping study and you want to understand the effect of doping on the lattice parameters, how are you going to do that? Well, X-ray diffraction will help you do that by doing a Rietveld refinement on X-ray diffraction patterns of samples that might have different doping levels and so forth. Okay, so that's what I expect you to understand, is what you can and can't get out of a Rietveld refinement, and to have a rough idea how a Rietveld refinement actually works. So anyway, I hope the video is worthwhile. Thanks.